Good afternoon, this is Schweitzer, and we're going to be using our linear relationships and proportions factor label with some chemicals now. We just, likely you've just kind of gotten around to the point where you are getting a little more comfortable setting up factor label type stuff, and we want to make sure that we are ready to just convert some stuff involving chemistry. So, a couple things here. One, we have mass, we have moles, and we have particles. What do these mean? Well, particles obviously are like atoms, molecules, could be maybe ions. So these are just individual particles. And you should note that really, whenever we look at chemical reactions, we balance them, say X plus 2Y yields Z. These little numbers here, which we balanced maybe all the way through middle school, ones and ones, are really the number of particles that a particular reaction is using. So, with not getting too much into this, chemical reactions are run based off numbers of particles, not the mass of the particles. So there are lots of examples in everyday life that you can describe this as. Sometimes I make the analogy: if you have 1,000, pounds. That's not pounds. 1,000 pounds of steering wheels. How many cars do you have? Really, that's a designation of a number. We want number of steering wheels, not the mass. If you have 1,000 pounds of people, how many people do you have? You could make an analogy. If you have 10,000 pounds worth of cars, how many cars do you have? If you need to transport people, how many people can you transport with 10,000 pounds worth of cars? The weight has nothing to do with it. You need to know the number of cars that you have. And if each car can fit 4 people, then you could transfer 4 people per car, but you need to know the number of cars. And that's really how all of chemistry works. So we have these numbers of particles. Now, what the heck is a mole? Well, it turns out that particles, man, they're just frustratingly small. These are so small. Every single breath that you take contains 1 to the 10th, or it's like 1 to the 10th particles. Okay, so it's a huge number of particles. So, with that being said, if particles are so small, then how do we deal with them? Well, what we do is we package them into like a dozen. So a particle to a mole is like 12 is to a dozen. A dozen. Okay, so 12 donuts equals 1 dozen. That way, again, is it the same thing? Yeah. You have 1 dozen equals 12. Okay. So it takes a number and packages into a number that contains more. So it's really a lot like 12 inches equals 1 foot. It's really the same thing. They're equivalent. So in this case, particles are a number of things. Okay, and moles are also a number of things. You could have 1 mole of donuts. Okay. You could have 1 mole of girlfriends. It's a number of things. Okay? So these are really the same thing. It's just a matter of we package them a little differently and we use them a little differently. Don't make a mole more than it is. With that said, how much is a mole? So the relationship between these two is never going to change. Just like 12 to 1 of a dozen is never going to change. So 6.0 1 mole equals 6.022 e to the 23rd things. And it doesn't matter what it is. It's a thing. Could be an atom, could be a molecule, could be an ion. Just that's sometimes we describe it. Could even be, like I say, even a formula unit. And that would be something that would be ionic. So an atom might just be an element like gold. How many atoms of gold do we have? How many molecules of water do we have? How many ions do we have? How many formula units? NaCl for ionic compounds. But this conversion never changes. It's just a conversion. Even if you don't know what a mole is, it's just number of particles, you could still use this conversion. Okay. Now, let's go to mass. Like I said, there's a major problem here, in that these particles don't really even use mass. 1x and 2 y's make 1 z. Alright, well, how much mass to use? I don't know, and at this point I don't really care. Just these could be bricks, these could be feathers. Maybe I use 10 grams of this and 0.11 grams of this. The weights are irregardless. The weights come from literally the number of neutrons and protons inside the nucleus. So if that's the case, then really that's all that determines the weight. For example, a hydrogen atom, okay, let's say a hydrogen atom and an oxygen atom, both one atom. And we can use these to make water. But the oxygen atom is 16 times heavier, which means it has 16 times more protons and neutrons inside of its nucleus, which just makes it heavier. That's fine. It's fine. So water, H2O, that means most of the weight of this water molecule is due to the oxygen, not the hydrogens, even though most of the particles, 2/3 of the particles, are due to hydrogen. So 2/3 of the particles are due to hydrogen, but in this case, 1/8 of the weight. Okay. Either way, so how do we go back and forth between these things? We have this term which is called molar mass. Okay, and that's pretty simple. It just means it's the mass of 1 mole. It's the mass of 1 mole. Okay, that doesn't seem like we're that much closer to finding out how do we know how much things weigh. So really we need to sort of give an idea of what's my sort of like my weight, oops, a little thinner here, my weight per particle, you might say. Like how massive is it? You could say you have 1,000 pounds of people. Well, what's the weight of your people? If they're each 200 pounds, well then you got 5 people. So really I need to know kind of my weight per particle. And that's kind of what we're doing here. So this is the mass of 1 mole. How do we know the mass of 1 mole? Alright, so this is what we did. This number here is chosen very uniquely so that when we look on the periodic table, we're going to see 2 numbers. Let's say oxygen. 8 would be the number of protons. We got 15.99 up top. This is the number of AMUs per atom. Now on average that would give me 8 protons, and on average we would get 7.999 whatever. I'm going to just round that to 16. Okay, 8 neutrons. Okay, that's fine. So we got most oxygen atoms are 16 AMUs per atom. That tells you how much it weighs. Hydrogen, on the other hand, is 1.000 and 1, so that means there's 1 proton, and it is 1 AMU per atom. This is where I'm getting the 16 times heavier. Okay. So for 2 particles, one weighs 16, one weighs 1. Alright. So this particle, this number is chosen very uniquely so that the AMUs per atom, often called the molecular weight, equals the grams per mole. And that's what we want. So let's take a quick moment here and let's calculate out some grams per moles. Okay. How do you go about calculating a molar mass? Alright, let's type that in here. How do I get my molar mass equivalency? Okay. So let's try it out once. It's pretty straightforward. Once you get a couple of these, you'll see how it works. And then that's going to be used to just do your... We still haven't converted anything. So for example, water. So this guy is 1.0, and there's 2 of them. I got that from the molecular weight. This guy here is 15.99, or 16, and there's 1 of them. Add it up. 2 times 1 is 2, plus 16 equals 18. That's AMUs per molecule. That means if you were to combine the protons and neutrons of the nucleuses, you'd have 18 of them. Okay? 16 of them came from the oxygen, 2 of them came from hydrogens. But that is equivalent to 18 grams per mole. Now, this is interesting here because if you have 18 grams per mole, how much water do you have? How much mass of how many moles do you have? And the answer is none. This is, you don't have anything yet. This is just a relationship. This is where we're starting to get into where it's like, okay, if you're traveling 80 miles per hour, how far did you go? Well, you don't have no idea. All right, it's just a relationship. So this is a flipper. You got a mass and you have a number of particles, and it just flips between the two. If by chance you have 1 mole, then you get 18 grams. But if you only have a half a mole, then you have 9 grams. Okay. If you got a tenth of a mole, you have 1.8 grams. So in this case, all right, we just add it up. So let's do one more quick example of this. Let's do, let's say, let's do aluminum hydroxide. Okay, I'm going to do that. So I guess I'm going to add these things up. So aluminum is about 26.9 something. And then we have, now how I can want to do this one is up to me. I can do 3 times 16, and 3 times 1, and then add them up. Or I could add this whole thing into 1, and then multiply times 3. Let's do that. 16 plus 1 is 17. 17 times 3 equals 51. All of this is 51, and the 27. And 878. That's 78 grams per mole. Now again, that's just my equivalency. I haven't even done anything yet. Okay, let's go to the next page and try some examples with this. Okay, so now, this is sort of my roadmap. I'm going from atoms to moles and moles to atoms back and forth. And then the next slide here, we'll do some grams. Okay, so work our way back and forth. Take a moment, try some of these. All right, what is the relationship that we have here? I'm going from moles to molecules, so I need to do just this guy. Grab my pen again. 1 mole is equivalent to 6.022 e to the 23rd. Of course, you could put that in your note card. Let's put the work here. I got 2 sig figs here. So 2.5 moles. Get rid of moles. And go to molecules. I only use molecule because O2 is a molecule. Now, this is my equivalency. So I'm either going to be multiplying by this number here. We call this Avogadro's number. Avogadro's number. I'm either going to be multiplying by it or dividing by it. Let's see, we got here 1 mole is equivalent to 6.022 e to the 23rd things. And you can go ahead. I'm not going to worry about the answer here. You should understand that you're just taking this base number 6 times 2.5. So let's do that once. 6 times 2.5, 6.022 times 2.5 is 15.0. So if on the rules of exponents, take this number times the base number is going to be 15, and I just take one. There's e to the first, or e to the 0. 0 plus 23 is just 23. E to the 23. There you go. That's equivalent to 1.5 e to the 24th. So hopefully your exponents are making sense. This guy here, okay, 3.1 e to the 23rd atoms. Now I'm going back the other way. Dot line, get rid of atoms, and I want to go to moles. 1 mole always equals 6.022 e to the 23rd. Divide it out, and we get 0.5 equals 0.50. I'm going to hold one more sig fig here because I have 2 there, I want 2 here. Take a second, try this on your own. Alright, so we got 100.0 moles, dot line, get rid of moles, and go to molecules. Formula units. It doesn't mean much, just that's the type of particle it is. It's ionic compound, 1 mole, 6.022 e to the 23rd. And 6 times 100 is 600. Okay, so 602 e to the 23rd is my answer, or 6.022 e to the 25th would be my same equivalent value. This guy right here, okay, 3.1 e to the 50th molecule, so I have more than 1 mole. Dot line, get rid of molecules, and go to moles. 1 mole is 6.022 e to the 23rd. And what do I got? So I'm going to just divide these. Now subtract 50 from 23. So you can type the whole thing in your calculator. You can use the rule of exponents. 3.1 e to the 50th divided by 6.022 e to the 23rd. And I get 5.1 e to the 26th. Which of course is those guys subtracted. That's my answer. Next one. Okay, now to do these guys is 2 steps. Go from moles to grams. You need to know how much 1 mole weighs. Oxygen times 2 is 32 grams per mole. Sometimes I like to put them in parentheses above. Let's do the work here. 2.5 moles. Get rid of moles and go to grams. This is my equivalency. This is the molecular weight. 1 mole is equivalent to 32 grams. 2.5 times 32 is 80 grams. Next one, going back the other way. Now this guy here, for gold, we need to look at the molecular weight for gold. It's like 207, I believe. 196.9, so I go 197. Alright, so 200 grams. Grams to moles. 1 mole is 197. Now I never memorize really if I'm dividing or multiplying by that molar mass. I use factor label. It tells me. Here it told me to multiply. Here it told me to divide. I do know that 200 grams is what I have. I know 1 mole weighs 197 grams. So I know that I have a little bit more than 1 mole. So if I multiply the two, I have some really large number, which is not going to be correct. So it's good and important to realize, just to estimate, 200 divided by 197, it's just a tad more than 1. I got 4 sig figs here, so we're going to go 1.015, and that is moles. Take a moment, try the other two. And there are lots of examples in your workbook that you should be trying, because watching me do it doesn't make you proficient. Doing 2 of them doesn't make you proficient. You got to do a bunch of them and try them out. Alright, so the NaL3 is cut this guy out. This guy is 23. This guy is 14. This guy is 16 times 3 is 48. Add all those up, and we get the molecular weight or molar mass of sodium nitrate. 85. 85 grams per mole. Okay, so I have more or less than a mole. I have more than a mole. So I'm expecting a number just over 1. 100.0 moles. Get rid of moles and go to grams. 1 mole is equivalent to 80. 1 mole is 85 grams. Okay, so I have 1 mole is 85 grams, so I have 100 moles. So I got a big number here. 85. I misestimated to begin with, which is important because then you know if it's not coming out right. And you can go backtrack and see if it's fine. Should be 100 times 85, which is 8,500. And that is what I'm looking for. Probably didn't even need a calculator there. 90 grams back to moles. Okay, 1 mole, carbon is 12, oxygen is 16 times 2 is 32. Add them up, I got 44 grams per mole. I have more than 1. I have more than 2. 2 would be 88. A little bit more than 2, not much. I don't have 3. So I expect a number just more than 2. 90 grams. Grams to moles. 1 mole is 44. 90 divided by 44 gives me 2.04. Okay. 2.04 moles. Again, your workbook is full of these problems. You should be trying them to make sure you are not only proficient, but proficient under pressure. I mean, you can do this no matter what. Thank you.